Alright, welcome everybody, and today we're going to talk a little bit about what it means to raise an imaginary power to a number. Right, so we're talking about numbers like 2 raised to I or 3 raised to 2I and numbers like that. And more specifically, I want to see where exactly these numbers lie in the complex plane. If we have a complex plane, where do these numbers exactly lie? Now we already kind of have a fair idea of what exponents mean in terms of real numbers, right? So if we have 2 raised to 4, we know that we write this as a successive multiplication, which written geometrically means successive stretching of the number line. Right, but this kind of a notion becomes, nonsensical when we talk about 2 raised to I, because, well, how are we going to multiply 2I times? Because I is not a counting number, right? So that's what we're going to discuss. And as we delve deeper into this territory, what we'll find is this way of looking at exponents as successive stretching of a number line is really just a special case of a much larger, much general transformation going on in the complex plane. Okay, so let's get into it. So we have our complex plane here, and for now I'm going to talk about numbers like e to the 2i and e to the 3i. I'm going to tell you why e is so special in a minute, but for now just bear with me. We'll talk about this first. Okay, so let's focus on this number first. There are a couple of ways of looking at this, but the way I like to do it is I like to locate 2i on our plane. Okay, 2i right here. And what this operation e does is it takes this point and it maps it. It maps the point onto a unit circle, right? And unit circle is just a circle with radius 1. So I have this here, and what e does is it takes this point and it maps this point onto some point on this circle. So say somewhere over here, right? E. And this point is chosen such that this point makes an angle of exactly 2 radians with the positive x-axis, because we're talking about 2i. And if we were talking about e raised to 3i, then it would take this point and again transfer it onto this unit circle so that it makes an angle of 3 radians. 3 radians. It's not really visible, but an angle of 3 radians with the x-axis. And similarly for every other point, every other point has its corresponding point on this unit circle. So really what e is doing is it's taking this vertical line and it's sort of transforming this line onto the circle, right? And one interesting thing to note here is consider this. Consider e to the 2 plus 2 pi I. Now what happens here is, well, 2 plus 2 pi I lies somewhere over here. So again, this point is transformed or mapped onto this circle, and the angle by which we're going to rotate this is 2 radians plus 2 pi radians. So 2 radians till here, and 2 pi radians is a full circle. So again, we landed at this point again. So what this means is this point is simultaneously e raised to 2i and e raised to 2 plus 2 pi I. Right? So really this line is kind of looping itself onto this unit circle. And this holds for every other point on this plane. For instance, if we have another point, say 2 plus 3i, 2 plus 3i, what e does to this is, again, it does map it onto a circle, but the difference is here the circle is much larger. right? And it just so happens that the radius of this circle is e squared. The radius of this circle is e squared. And the rotation property still holds, right? You still have to consider this point and rotate it by 3 radians to actually get e to the 2 plus 3i. Right, so the farther the point is from this vertical line, larger the circle is, and farther to the left the line is, or the point is, smaller the circle gets, right? So we had a unit circle here. So if we had considered some point over here, then this corresponding circle would be smaller than this, right? Right, and if we're considering this entire vertical line over here, then really what this is doing is, again, taking this vertical line and it's sort of transforming it onto a circle. So a really nice way of looking at this is E takes every vertical line on this plane and it curls them into a circle. So that's sort of a space transformation that we think of when we discuss E. All right, so that was E. Now, what if you were told to find log of 2 plus 3i? And log is just the inverse function of E. So instead of assuming it to be on a vertical line and then transforming it onto a circle, what you do here is you assume it to be on a circle in the first place. It's not very well drawn, but yeah. Circle, and then because you know the radius of this circle and because you know this angle, you can figure out what line this circle is corresponding to, and from that line, maybe it lies somewhere over here, and from that line you can find out the log of 2 plus 3i. Now, an interesting thing to note here is ln 2 plus 3i, or any number really, has more than one solution. It has an infinite number of solutions. Try to think of why that happens, and try to convince yourself of why that's the way it works. And that's kind of a brain teaser I'll leave you with. Anyway, so the last thing I want to discuss is this number e. Right, I told you at the beginning we're only considering e for the moment. And the reason I considered e to the 2i and not, say, 2 to the 2i is because, well, remember how here, when we chose 2i, we got to sort of rotate this point exactly by 2 radians, and for 3i exactly 3 radians. For 10,000 i, we can rotate it by 10,000 radians. That sort of a transformation only holds for e. If I took 2 to the 2i, then again this would transform this entire line. It would be transformed into this unit circle, but the angle with which you would have to rotate it to get the correct answer would be something different, right? And it's only for e that this special property of this direct sort of rotation holds, and that's why e is considered special. And actually that's why one of the most beautiful equations in mathematics, e to the pi I plus 1 equals to 0, this is the reason it works, because what this is essentially saying is choose the point pi I, which is, I don't know, here, pi I, and what e does is, again, it transforms this point or maps this point onto this unit circle, and such that this is transformed, or this point is mapped onto the circle such that it makes an angle of pi radians, or 180 degrees, with the positive x-axis. Which means when you do e to the pi I, this point is transformed into this point, which is exactly -1. And that's why e to the pi I becomes -1, right? And so this is why this equation works. Anyway, so hopefully you had a little bit of more insight into how to deal with imaginary exponents and hopefully you now know how to visually represent these numbers and how to deal with them. See ya. Bye.